305 in the journals, right? That's I'm wrong, 305, yeah. We're going to write down 3 of the vocab terms, and we're going to skip one of them, just for the sake of time. Now, luckily, again, on this note sheet, we're almost done with this chapter, guys. We got 2 sections left. Today's and then 10.7. This is one heck of a big chapter, and I understand that. So is next chapter, but at least next chapter is split up into 2 tests. You have a test over this stuff Wednesday, April 26th. That's next Wednesday. Just a heads up for you. So last week, not last week, that is false. Yeah, last week, I'm correct. In 10.5, we covered those 3 theorems, and then we reviewed them on Tuesday before your big ACT day. So with those 3 theorems, we were looking at angle relationships and some of those theorems inside of a circle. Today, we're going to be looking at segment relationships and some of those theorems inside of a circle. A lot of it's algebra today. At the beginning of the chapter, we did a worksheet on foiling and factoring, and you're going to have to use that today as well, or the box method, I guess, and then the little X thing with the factoring. First little vocab here, there's going to be 3 theorems we're going to talk about today. First one here, in history, we have not had any issues with this theorem with my classes, like typically. I don't want to promise everyone has not had issues, but most people don't have issues with this theorem. But let's talk real quick about segments of a chord. You're probably going to hear me refer to it as pieces of a chord, just so you know. So chords, to review that, because that'll be on your test, chords start and stop on a circle. They are segments that directly lie inside of your circle. This is on your vocab, by the way, page 305. So the segments of the chord, when you have 2 different chords that intersect, they're kind of cutting each other into pieces, not necessarily equal pieces, but they're cutting each other into pieces of a chord. Okay, so our first theorem here, you have 2 different chords lying inside of this circle. So just to review again, chords start and stop inside the circle. So there's an example of one chord, and then here's an example of another. When 2 chords intersect, anywhere that they are, they could go through the center, they don't have to, they could be wherever. When they intersect, they split each other into pieces that aren't equal, but the products of those pieces will be equal. So if we look at this chord right here, this green one, it's being cut into 2 different pieces. AE and EB. If we multiply those together, AE and EB, it's going to have the same exact product, same exact final number, if we multiply these 2 pieces together of the other chord, DE and EC. Okay, so again, the chords are splitting each other into pieces that when you multiply those pieces together, those products will be the same. So like number 1, for example, here's our 2 chords. Here's one chord, and here's the other chord. Okay, let's just look at the green one first. It doesn't matter which one you look at first, but the green one. The green one's being cut into 2 different pieces at this intersection point, X and 3. So we're going to go ahead and multiply X times 3 together. That product of those 2 pieces has to be the exact same product as the second chord if we multiply these 2 pieces together, 4 times 6.
Why would you just add them?
Well, I mean, you would get 10 and X plus 3, but like those don't equal each other. Like you're not going to get the right X here if you do that. I don't know if that answered your question or not.
I'll probably figure it out later.
Okay. The theorem is the pattern that always happens here is that anytime you have 2 chords and they intersect, the products of the pieces are the same, not the sums. Okay, so then from here we get a little bit of algebra. X times 3 is what? 3x. 4 times 6 is 24. Divide by 3 and x is 8. So Isaiah, if you would have added them, you would have gotten x equals 7, which is not correct. So that theorem wouldn't work. Okay, on our second one, same thing. Here's one chord. Let's go ahead and multiply those two pieces of the chord together. And you have to use the pieces that are on the same chord, so meaning collinear. They have to be on the same line. So we're going to multiply 2 times, okay, be careful here, x plus 1. You're going to multiply 2 times the entire thing x plus 1, not only times x. You're multiplying it times the entire binomial. And then on the other chord, the two pieces are 4 and 3 that you'll multiply together. So again, when you have a binomial, two terms like that, make sure that you're distributing properly. On the left side, 2 times x is 2x, 2 times 1 is 2, 4 times 3 is 12. This is the easy algebra, that's why I'm going through it so quickly. Hopefully you're following along, okay? First step, minus 2. You get 2x equals 10, divide by 2, and x equals 5. And these don't ask you to plug in or anything, so we don't need to worry about that. Sometimes they say, like, find the measure of AB or whatever, find the measure of the chord, but we don't have to here. Questions on those? Typically, those are pretty straightforward for people. Now, let's look at one where we're going to have to do some box method and some factoring and a little more algebra, okay? Let's start with this chord here, ML. We're also going to ignore the directions for the sake of time, and we're just going to find x, just so you know. I understand that they want us to plug x back in the end, but we're not going to for the sake of time. There are going to be 4 different problems on your homework tonight where you have to factor, so it would be very wise of you to not have anything else out in front of you right now as we do this problem. What are the 2 pieces of the red segment? The 2 different pieces of the red segment.
X plus 2 and x plus 1.
Okay, so we're going to multiply x plus 2 and x plus 1 together, so we're going to have to box that out in a second. And then on the other chord, x and x plus 4 are the 2 pieces that will multiply together. That one we'll just be able to distribute, but on the left side we're going to have to box them. DJ, can you make sure your earbuds out? On the left side, when I box this, remember that it doesn't matter which one goes on top and which one goes on the side, whatever one you want. It doesn't even matter which one goes in front when I initially write it. So I'm going to put the x plus 2 on top and the x plus 1 on the side, but it literally doesn't make a difference. So if you have the 1 on top, you're fine. And then we do our little box method. Most people, like on their old homework assignments, did fine with this. So in the first box, x times x is x squared. Second box, x times 2 is 2x. 1 times x is 1x. And then this final box, make sure, I still had a few people adding, make sure you are multiplying there. The whole box is multiplication. We're going to add the like terms though in just a second. Let's take care of the right side while we're here. If I distribute x through, what's x times x? What's x times x? X squared. X plus x is 2x. And then x times 4 is 4x. Okay, that side's taken care of. So we just need to clean up our little left side here, the box method. When you finish off your box method, you want to add any like terms, which for your guys' purposes will always be in the diagonal. It won't always be that way next year in Algebra 2, but for your purposes now, you're always going to add the diagonal terms. So we have x squared plus 3x plus 2 equals x squared plus 4x. Oh, this one doesn't involve factoring. I'm thinking ahead. This one does not involve factoring because what can we cancel on both sides that's 100% identical? Jake? X squared. We can go ahead and take that x squared away. Goodbye. And then we're left with 3x plus 2 equals 4x. We will have to FOIL today, but it wasn't this one. Huh?
What do you do with the 4x?
X times 4 when I distribute it up here. Before I go on, any other questions like that? Those are great questions. Like, where did this come from? How did you get this?
So the answer's just done.
No, I'm not done yet. Nope, I gotta subtract my 3x over, and then I get 2 equals 1x. You can some people like to divide by 1. You're not gonna get anything other than 2, but if you wanna add in that extra step of dividing by 1, you most certainly can. And your answer is 2. Now in this problem, technically they want you to plug 2 back in and find the lengths, but for the sake of time, we're gonna skip that. Are we okay with that? I know, you're devastated that we're skipping a step in math, but almost dropped my marker. Okay, questions on that theorem. This is the one that people typically do okay with. Just make sure you're using the pieces that are on the same line together. Occasionally each year I'll have people do like x times x plus 2. Don't use any that are not collinear together. All right, our second theorem here is going to involve some secant segments. So let's go over what secant segments are and what tangent segments are. We're going to skip external segment on your vocab, so these will be the last 2 vocab terms. The tangent segment. Now a tangent, going back to section 1, a tangent's always on the outside of your circle. So it intersects in one point. So when we talk about a tangent segment, we're only talking about a piece of the tangent. So it's going to start on the outside and then go up to the circle and stop. Tangents never go through the circle, ever. So it'll be outside the circle, go up to the circle, touch it, and stop. And then a secant segment, secants normally go all the way through your circle, and they're normally lines that go on forever and ever and ever. So a secant segment is going to be just a piece of your secant, and specifically it's going to start on the outside of the circle, go through the circle, and then stop. And you'll see what I mean in just a second. So in other words, for today, your tangent segment will always be solely on the outside of the circle, and then your secant segment will be a segment that starts on the outside but then goes through the circle. Now, the one vocab term we didn't cover, the external segment, you're just going to hear me refer to it as the outside piece. You're going to see secant segments today that look like this. The external segment is just the piece that's on the outside. External means outside. So the piece of the secant that's on the outside of the circle would be your external segment. But we don't need to write that down. So if you're writing this down, I told you you didn't have to, so don't worry about it. But that's what we're looking at today. So you're going to hear me say tangent. You're probably just going to hear me say the tangent piece as opposed to segment. And then you'll see a secant segment that goes through the circle. First theorem with this is involving the secant segments, 2 secant segments. Here's one of them, EB, and here's the other one, ED. So our theorem, you can see it here, but I'm also going to give you like an example so that those of you that this makes no sense, then you can have some like actual evidence and numbers here. And then I'm going to also put it into words. So when you have 2 secant segments that intersect, so they both go through the circle and they intersect out here, we have a theorem that says for each secant, the outside piece times the entire length, the outside piece times the entire length equals, on the other side, the outside piece times the entire length. Okay, it gets tricky because the theorem is not outside piece times inside piece. So if you are a person that's very auditory, you're going to hear me say this a lot over the next couple of days. Outside piece times the entire thing equals outside piece times the entire thing. Now, for those of you that are a little more visual, let me give you an example. These numbers are probably not going to be to scale, just so you know. But if you have something like this, okay, the theorem is not 3 times 4 equals x times 6. That is not what it is. What it would be in this case, if this were the numbers that were given, it's always the outside piece, so that would be like 3, times the entire thing. How long would this entire segment be? 7, 3 plus 4 is 7, equals outside piece, x, times, not times 6, but times the entire length. And how could I write this bottom one as one expression? X plus 6, right? Up here, how did I get 7? I added 3 and 4. So down here, when I write this entire thing, it would look like x plus 6, okay? So if you're a person that wants like an example in your notes, then you could maybe jot down some of those numbers, okay? But otherwise, you're going to hear me say this a lot today. Outside piece times the entire thing equals outside piece times the entire thing, not outside times inside. That's not how it works. You will not get the same answer that way. It's not proportions either, so don't try and set up proportions and cross multiply. Can I keep going? Is anybody still writing stuff down on this slide? Okay. So this is where we're going to have to do some foiling, but not just yet. So on this first example, let's just look at the top secant segment here. So again, we are looking at outside piece times the entire thing, times the whole length. So let's go, Holly. What's just the outside piece of RQ?
Oh wait, RQ.
Yeah, just the outside piece.
And then
9. So we're going to take 9 times, and she kind of gave it away here. The entire thing is 20. 9 plus 11 is 20. Not 9 times 11. That's not going to work. We will not get the right answer. Equals, on the bottom secant, Sam, what's just the outside piece of the bottom secant? 10. And then times the entire thing. So I'll open this up to everybody. How could I write this entire green segment as one expression? 10 plus x, x plus 10. It doesn't really matter which way you write it there. But you don't just want to take it times x, because then you're not going to get the right answer. Okay, on the left, we can do this in our head, this problem. 9 times 20. Think about 9 times 2, and then tack on a 0. What's 9 times 20? 180. Distribute the 10 through, we get 100 plus 10x minus 100. Again, I'm going through this stuff quickly because this algebra is piece of cake, hopefully. We're going to get to one that's a little bit harder. And then divide by 10, and we get x equals 8. But again, if you did 9 times 11 equals 10 times x, you will get 9.9. 9.9 is not the same thing as 8. So make sure you don't do outside times inside. Example 2, let's look at this top secant. Let's go, Jace, what's just the outside piece of the blue secant? 6. And Jared, what's the entire length? 9 is only the inside piece. What's the entire thing?
15.
And then on the bottom, Tanner, what's just the outside piece of the bottom secant? And then anybody, how could I write the red segment as one expression? X plus 5. Or 5 plus x, however you want to write it. It's not going to make a difference in the end. This one's pretty quick as well. 15 times 6. What's 15 times 6? 15 times 6. 90.
So,
Distribute, we get 5x plus 25. So now it's a two-step equation. Minus 25. We get 65 equals 5x. Divide by 5. 65 divided by 5 is
13. Is that right?
Mhm. Okay, questions before I get to the one that's a little bit tougher? No? Okay. This one gets a little bit tough with the factoring and box method stuff. Let's get it all set up here. So let's look at the top secant. Outside piece is 3. Now, the entire thing here, the way we get the entire length is to add the pieces together. So 3 plus x plus 2, 3 plus x plus 2 is going to look like this. So what would that simplify down to?
X plus 5.
X plus 5, because 3 times 2 is 5. Very good. Yeah, anytime you add 2 segments together, you're literally just adding those expressions together. And then on the bottom one, the outside piece is x plus 1. The entire length would be x plus 1 plus x minus 1. That's what you're doing there. X plus 1 plus x minus 1. So what's x plus x? 2x. And what's 1 minus 1? Nothing. So x plus 1 plus x minus 1 would just be 2x. This one doesn't involve the box method like I thought, but it is going to involve factoring. And it's not a nice factoring problem either. The ones on your homework that involve factoring are quick ones, like leading coefficient is 1. All right, let's distribute on the green side. 3 times x is 3x, 3 times 5 is 15. And on the blue side, what's 2x times x? What?
What did you say again?
Okay, 2x times x. What? Say again? Okay, you guys are saying correct things, Seth and Luke. What are you saying? What?
I don't know if this is right, but.
Just guess. Who cares?
X with like a little 3.
X cubed? Not x cubed, but x times x is x squared. So it would be 2x squared, which I thought you said, but I couldn't hear you. So I was genuinely just asking.
Okay. She's back.
And then 2x times 1 is 2x. Okay. After we distributed. Now, here, the x squareds are not going to cancel, and the x's are not going to cancel. And so since you can't cancel either of them, we're going to have to factor here. You cannot factor. This is going to take you back to Algebra 1. You cannot factor until you have it set equal to 0. That's what we have to do first. So I'm going to take all of this business on the left, and I'm going to move it over so that it's set equal to 0. You cannot factor. If you didn't make yourself a note for your homework, because you'll have 4 problems like this, you cannot factor until it is set equal to 0. So I'm going to move the 3x over. Oh, not there, though. And I'm going to move the 15 over as well. So that it's just 0 on the left, and then 2x squared minus 1x minus 15. That's what we've got now. Because you can't factor until it's all on one side. Now, bear with me. First hour was rough because this x thing is new to me, so I've only seen it once. So I think I can do this correctly now that I've done it first hour. So in your little x thing, your middle term always goes on the bottom, I believe. And then the top number is always the last term times the leading coefficient. So what's negative 15 times 2? Negative 30. Okay, so our goal here is to find 2 numbers that multiply to this and add to this. That's your goal here. You want to find numbers that multiply to negative 30 and add to negative 1. So let me list out just over here factors of 30. 1 and 30, 2 and 15, 3 and 10, 5 and 6. Those are all your factors of 30. I want to add to negative 1 though. So I need to pick the combination of numbers that could possibly give me 1. Right? Like this, you can take 30 plus 1 and 30 minus 1. You're not going to get 1 as an answer. 15 minus 2, 15 plus 2? No. Which combination here could give me 1? 5 and 6. Okay? One of those needs to be negative. If I want it to be negative 1, which of those needs to be negative? The 6 or the 5? DJ? The 6. 5 minus 6 would give me negative 1. This is, I have no problem with that. This is where I get a little bit tripped up. So have patience with me as I'm learning this. Okay, so in your little box, I'm going to put the 2x squared here. And I'm going to put the negative, no, I don't remember if it's the 30 or the 15. We're going to try the 15 there. We're going to try that. No, that's not right. Yeah, it is. Yeah, it is. We're good. Sorry. And then we're going to put 5 somewhere and negative 6 somewhere. So I'm going to put a 5x here and a negative 6x there. It doesn't matter which one the diagonals go in. All right, now we pull out leading or greatest common denominators. So what's our greatest common factor? Sorry. What's the biggest thing I can take out of 2x squared and 5x? Biggest thing I can take out of 2x squared and 5x. You take a 1 out, but you can also take out an x. What's the biggest thing I can take out of negative 6 and negative 15? Someone said it. Negative 3. Let's go and take that negative out as well. And then in the columns, what's the biggest thing I can take out of 2x squared and negative 6x? 2x. And then what's the biggest thing I can take out of 5x and negative 15? 5. You did it. I did it. I'm so proud of myself. That stuff is rough for me. We used to just do guess and check when I was your age. So, okay, so then your two factors are 2x plus 5 and x minus 3. You will not have any on your homework where the leading coefficient is not 1. So when the leading coefficient's 1, that makes things quite easier. All right, now the very last thing we have to do here is actually get an answer for x. That's not your answer. You didn't find x yet. So when we find x here, the only way for this to equal 0 is if this is 0 or if this is 0. The only way to multiply and get 0 is if one of your factors is 0. It's the only way to multiply to 0. So we're going to solve each equation here. I believe you did do things like this last year, so this should not be like completely 100% new to you. When we solve for x here, we get 2x equals negative 5, divide by 2, and we get x equals negative 2.5. And then over here, we just add 3. Those are your two solutions for that factoring. But one of those doesn't make sense in the problem. Which one would not make sense if we're talking about segment length? Negative numbers. You can't have negative lengths. So we're going to keep our final answer as 3. So one's on your homework where you're factoring. The leading coefficient is 1. So you're just finding two numbers that multiply to the last one and add to the middle term. A lot easier. I got to keep going for now, though. Okay, you won't have any quite like that, but you will have to do this on your homework. Like you'll get two factors, you got to set them both equal to 0, you got to solve for x. Why don't you stay turned around? Tyler looks very nice today, but just stay turned around this way. Just stay turned around this way. All right, last little segment here, or last little theorem here is going to be really, really similar to the last one, okay? The only difference is instead of having two secants, like two of them that go through the circle, now we have one secant and one tangent. The tangent goes to the outside of the circle and stops. It's going to work the same way though. On the bottom, on the secant segment, you treat this the same way we did the last one. You're going to do outside piece times the entire segment. Okay, that's not different from what it was before. Now, when you look up here at the tangent segment, same thing, outside piece times the entire thing. However, the outside piece of that segment, so the one that's not in the circle, and the entire length are the exact same segment. EA is the outside piece, and EA is the entire segment. So if you take EA times EA, you end up just getting EA squared. So we're just going to take that tangent piece and square it. But you're essentially doing the same thing, outside piece times the entire thing. Okay? So to finish this off, we're not going to get to the last question about the tank or earth, whatever it is. Aquarium tank. Thank you. Okay, let's look at this first example. I always start with the tangent piece. So which one of those is the tangent piece that's only on the outside of the circle and does never go through? No, the tangent piece is the one that does not go through the circle. X. We're going to start with that squared equals, and then on the top secant, this isn't going to work any different than it did before. So who have I not called on? Zach, what's the outside piece of the secant? 1, and then the entire length, Zach, is 4. So then we get 1 times 4 is 4. How do I get x by itself here? Square root. Now, normally, like last chapter, you got plus or minus 2. But since we're talking about a segment length, like x is a segment length, you can't have negative lengths. So our answer is just going to be plain old positive 2. Can't have any negative answers in this chapter, or in this section at least. Okay. On the second problem, Tyler, what's the tangent piece only on the outside of the circle? 7, so we're going to start with 7 squared. And then on the secant.
Good morning, Team 14. May I have you stand and please join me in the Pledge of Allegiance. I
Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Thank you. Have a seat. All right. Today is today's Titan Student Bulletin for April 20th. Yearbook orders. Deadline for ordering a 2016-2017 yearbook.
You can ask, like, Miss Kelly, could
Please
you
order
come here,
online or in room B10 before May 1st. The cost is $80. Attention juniors. If you're interested for running for senior class officer, please see Mrs. Lindsay in room F12 or Mr. Nienhauser in room A11 for election packet. And the 6 members, there's an NHS meeting in the library or at 3:30 p.m. in Mr. Marsh's room.
Hey, you guys can finish that off. Finish it really quick.
Students are not allowed in the PE locker room.
Finish that problem, guys. Finish that problem.
Administrator, coach, and or security personnel. Please do not go to a locker room with your items, books, homework, or contracts. Circle Friends. Help Circle Friends celebrate Autism Awareness and Acceptance Month by wearing blue on Thursday, April 27th. During the week of April 24th through April 28th, members will be outside of the lunchroom. Stop by, buy a bracelet, or participate in our Puzzle Piece Challenge. That's all for today, Titans. Have a slow Thursday. And always remember, come back to you.
Okay, Andrew, what's 7 squared? 49. Quiet down, please. Stop talking. 5 times 5 plus x is what?
25 plus 5x.
Okay, minus 25 over. You get 24 equals 5x. Divide by 5. And you get x equals what?
Oh, it's going to be decimal.
It is going to be decimal. What is it? 4.8?
Yeah,
So,
4 and 15.
Hey, Seth.
4 and 4 6.
Great. Everyone needs their 10.6 worksheet in front of you, so I can tell you which ones you got a packet on. Every single person needs that 10.6 worksheet from the packet out in front of you.
Every single person.
Every single darn person. 10.6 worksheet, get it out in front of you. Just leave your journal, Luke. I'll take care of it.
You asked so kindly.
Hold on, I need to find my worksheet. Okay, can I borrow this? Here are the ones you gotta factor on, ready? Number 3, you gotta factor.
Okay, but
So when I say that you have to factor, that means that you just set it equal to 0 and then factor. Tanner, can you go sit down and fill this in like I'm telling you to? Number 3.
What's different over there again?
maybe if you were listening.
Okay, I only want to say this one more time. Number 3, you need to factor. Number 6, you're going to have to factor. Number 12, you're for sure going to have to factor. And number 7. So again, 3, 6, 7, and 12.
8, 6,
And then you won't have any new homework tomorrow after the scavenger hunt, so I put a note in the sub-notes that if you guys get done with that early, you need to make sure this is done for Monday. I don't want any more excuses about why you didn't get your homework done or why you didn't take care of your responsibilities. You got business to do, get your business done before Monday. What?
No. What's that?
Tyler, you won't go jumping downstairs, bro. 20 minutes late. Let me go.